For most of the 20th century, Pluto sat at the edge of every diagram of the solar system as a kind of afterthought, a tiny frozen dot too far away and too small to matter much scientifically. Then, in the summer of 2015, a spacecraft that had been flying through space for nearly a decade finally got close enough to actually look, and what it found broke almost every assumption planetary scientists had carried about that tiny frozen dot for generations. Pluto wasn't dead. It was doing things no one expected a world that small, that cold, and that far from the sun to be capable of doing at all. And in some cases, scientists still don't fully agree on how. Pluto was discovered on the 18th of February, 1930, by a 24-year-old amateur astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona, painstakingly comparing photographic plates of the night sky taken days apart, searching for anything that appeared to shift position against the fixed background of stars. He found his moving point of light after months of tedious searching, and the discovery made him instantly famous, a young man from rural Kansas credited with finding a new member of the solar system. Tombaugh died in 1997, decades before any spacecraft ever got close enough to see the world he'd found as anything more than a faint, unresolved dot, even through the most powerful telescopes then available. When New Horizons finally launched in January of 2006, mission engineers placed a small canister containing a portion of Tombaugh's ashes aboard the spacecraft, meaning the astronomer who discovered Pluto ultimately became the first human being to travel there himself, even if only after his own death. Arriving at the world, he'd found photographed on a glass plate 85 years earlier. See, to understand why the discovery landed so hard, you first have to understand exactly how hostile an environment Pluto actually sits in. It orbits the Sun at an average distance of roughly 9 billion kilometers, close to 40 times farther out than Earth, a distance so extreme that sunlight arriving at its surface is only about 1,000th as intense as what you'd feel standing outside on Earth at noon. Surface temperatures hover around minus 230 degrees Celsius, cold enough that nitrogen, an invisible gas that makes up most of the air you're breathing right now, exists on Pluto not as a gas or even a liquid, but as solid ice, hard as rock underfoot. For decades, the standard model of planetary science treated a world with those characteristics small, distant, and that cold as a near certainty to be geologically inert, a frozen leftover from the solar system's formation with nothing left happening beneath its surface. Mercury, the Moon, and Mars, all considerably larger than Pluto, had each gone geologically quiet billions of years ago, their internal heat long since radiated away into space. A body as small as Pluto, roughly 2,377 kilometers across, smaller than Earth's own moon, should have cooled off even faster. That was the reasonable, well-supported scientific consensus heading into 2015, NASA's New Horizons spacecraft, launched in January of 2006, spent 9.5 years crossing the solar system specifically to test that assumption. And on the 14th of July, 2015, it finally got its answer, though not in the leisurely way most planetary missions gather data. New Horizons wasn't built to slow down, enter orbit, or take its time. It screamed past Pluto at roughly 49,600 kilometers an hour, coming within about 12,500 kilometers of the surface. And the entire close encounter, the only real chance humanity would get to study this world up close, lasted only a matter of hours before the spacecraft continued on into deeper space, unable to turn back for a second look. Everything scientists know about Pluto's surface in close detail comes from that single brief pass painstakingly transmitted back to Earth over the following 16 months, since Pluto is so far away that even data traveling at the speed of light takes over 4 hours to arrive. The image that immediately reshaped how scientists understood this world was a massive, pale, heart-shaped region now informally called Tombor Regio, honoring Clyde Tombaugh, the astronomer who first discovered Pluto in 1930. Its western lobe, an enormous plain of nitrogen, methane, and carbon monoxide, ice roughly 1,000 miles across, was given the name Sputnik Planitia, and at first glance, in the early low-resolution images, it looked almost unsettlingly smooth, nearly featureless. That smoothness alone should have been suspicious to anyone paying close attention, because in a solar system where small, cold bodies are typically covered edge to edge in impact craters, accumulated over 4.5 billion years, a surface this clean implied something was actively erasing the scars. When higher resolution images finally came through, scientists found their answer, and it wasn't what anyone expected. The plain wasn't actually flat or featureless at all. It was divided into thousands of irregular polygon-shaped cells, each one roughly 10 to 40 kilometers across, separated from its neighbors by shallow troughs, a pattern that looked uncannily similar to the surface of a slowly simmering pot of oatmeal as it cools. That resemblance turned out to be far more than a coincidence. The cells are genuine convection patterns, meaning the nitrogen ice inside Sputnik Planitia is actively, physically churning warmer material rising from deeper layers toward the center of each cell, spreading outward across the surface, cooling and sinking back down again along the edges. In a slow motion cycle, scientists estimate takes somewhere in the range of several 100,000 years to complete a single full rotation. It's a genuinely strange thing to reconcile with a world sitting at minus 230 degrees Celsius. Frozen solid, in the everyday sense of that phrase, doesn't mean motionless on Pluto, at least not everywhere. Part of that same plane is turning over on itself, continuously, right now, which is precisely what keeps it looking so remarkably young. Researchers estimate the visible surface of Sputnik Planitia is less than 10 million years old, a genuine blink of an eye set against the roughly 4.5 billion year age of the solar system as a whole. That single observation forced an immediate, uncomfortable question. Convection like that requires a genuine heat source underneath it, some form of energy pushing material upward from below, and Pluto, on paper, shouldn't have one. Unlike icy moons such as Europa or Enceladus, which stay geologically active because they're constantly flexed and squeezed by the powerful tidal pull of a nearby giant planet, Pluto has no comparable neighbor exerting that kind of gravitational stress on it. The Sun, from Pluto's distance, provides essentially no meaningful energy at all. The most plausible remaining explanation is residual internal heat left over from the radioactive decay of unstable elements buried in Pluto's rocky core, the same basic mechanism that keeps Earth's own interior warm. The trouble is that a body as small as Pluto should have radiated that internal heat away into space long ago. According to standard models of planetary cooling, the same models that correctly predict Mercury and the Moon going geologically silent billions of years ago. Pluto appears to be defying that math. And as of the most recent published research on the subject, there's no fully settled explanation for exactly how it's managing to hold on to enough internal warmth to keep an entire nitrogen ice plain slowly convecting after 4.5 billion years. Sputnik Planitia wasn't the only surprise. Along its western edge, New Horizons photographed genuine mountain ranges, some peaks rising more than 3,500 meters above the surrounding terrain, comparable in height to sections of the Rocky Mountains. These mountains aren't made of ordinary rock, though. At Pluto's extreme temperatures, water ice behaves mechanically almost exactly the way silicate rock does here on Earth, rigid, strong, and structurally capable of holding up genuine mountain-scale terrain rather than slumping and flowing the way ice does in warmer environments. What struck geologists most wasn't simply that these mountains existed, but how sharp and clean their edges appeared in the images. A strong visual signature of relatively recent formation, likely within the last 100 million years or so, rather than terrain that simply sat there, slowly eroding since Pluto's formation. Something, recently by geological standards, pushed that material upward. Then there are the glaciers, and this is where Pluto's behavior stops resembling anything else typically associated with a small, frozen world at all. These aren't water ice glaciers of the kind found in Antarctica or Greenland. They're rivers of solid nitrogen ice flowing, however, imperceptibly slowly to a human eye, down out of Pluto's highlands and pooling into the lowlands of Sputnik Planitia, carving visible channels and leaving flow marks in the surrounding terrain in a pattern immediately recognizable to any geologist familiar with how glaciers behave on Earth, just built from an entirely different material at a temperature nearly 200 degrees Celsius colder than anything Earth's coldest glaciers ever experience. One particular feature pushed the conversation even further into territory that's still genuinely disputed among researchers. In Pluto's southern hemisphere, New Horizons imaged a broad, dome-shaped structure called Right Mons, roughly 150 kilometers across and about 4 kilometers tall, with a distinct depression at its summit bearing an unsettling resemblance to a volcanic caldera. A second, similar structure nearby, Picard Mons, shows comparable characteristics. Neither feature has any confirmed impact craters on its surface, itself a strong hint of relatively recent formation, and the leading hypothesis among the New Horizons science team is that both are cryovolcanoes, structures built not by molten rock the way volcanoes on Earth are, but by slow eruptions of an icy slurry, likely some mixture of water ice, ammonia, and possibly nitrogen or methane, extruded from beneath the surface with a consistency researchers have compared to thick toothpaste. It's important to be honest about the state of the evidence here. Cryovolcanism on Pluto remains a genuinely active area of research and debate rather than settled fact, since confirming an actual eruption event, rather than simply an unusual dome-shaped landform, is extraordinarily difficult from a single brief flyby's worth of images. But if the interpretation holds up under continued study, it would mean Pluto has been resurfacing parts of itself, not just through slow ice convection, but through genuine eruptive activity, something almost nobody studying the outer solar system expected to find on an object this small and this cold. All of this forced a genuine reckoning with one of the more comfortable, long-standing assumptions in planetary science, that a world's size is a reasonably reliable predictor of how geologically active it remains. Mercury is meaningfully larger than Pluto and has been geologically quiet for billions of years. Earth's moon, also larger, shut down its internal geologic engine long ago as well. Mars, larger still, shows only faint, ambiguous hints of anything beyond ancient, long-dormant volcanic activity. By that pattern, Pluto, smaller than all three, should have been the most inert of the group, not the most active. Instead, it's the one still visibly reshaping its own surface. Nobody currently studying Pluto claims to have a fully settled explanation for how a body this small manages to sustain this level of ongoing geological activity, so far past the point where standard heat retention models predict it should have gone cold and still. It's one of the genuine, openly acknowledged gaps in current planetary science, not a mystery solved quietly in a footnote somewhere. The atmosphere added its own layer of surprise entirely separate from the surface geology. Pluto's atmosphere is extraordinarily thin, with a surface pressure roughly 100,000 times lower than Earth's, composed mostly of nitrogen with traces of methane and carbon monoxide. When New Horizons looked back at Pluto's night side several hours after closest approach, backlit by the distant sun, it captured something nobody had predicted: layer upon layer of atmospheric haze extending far higher into the sky than any pre-flight model had anticipated, in some images reaching altitudes of over 150 kilometers, arranged in more than a dozen distinct horizontal bands. When the first color images of that haze came back, they revealed something even stranger. The sky above Pluto is blue, produced by the same basic principle of light scattering that makes Earth's own sky blue, though the underlying chemistry is completely different. On Pluto, ultraviolet sunlight striking methane and nitrogen molecules high in the thin atmosphere triggers a chain of chemical reactions that build up small, soot-like organic particles called tholins, and it's those particles, not simple air molecules the way it works on Earth, that end up scattering blue light back toward an observer. Those same tholins, once they eventually settle down through the atmosphere and accumulate on the surface, are responsible for much of Pluto's distinctive reddish-brown coloring. That thin, hazy atmosphere turned out to be doing more than simply looking beautiful in backlit photographs. That thin, hazy atmosphere turned out to be doing more than simply looking beautiful in backlit photographs. Its behavior is also tied to a genuinely strange seasonal rhythm unlike anything experienced on Earth. Pluto takes 248 Earth years to complete a single orbit around the Sun, and its axis is tilted at a steep angle, meaning different regions of the planet spend decades at a time in continuous darkness or continuous sunlight as it slowly makes its way around. When a given region moves into its long winter, temperatures drop low enough that atmospheric nitrogen and methane gas freeze directly out of the sky, falling as frost and thickening the surface ice, effectively causing Pluto's already thin atmosphere to partially collapse. As that same region eventually rotates back into decades of continuous sunlight, the ice sublimates back into gas, thickening the atmosphere again. New Horizons happen to catch Pluto during a relatively active point in that immense multi-decade seasonal cycle, meaning the atmosphere and haze layers photographed in 2015 represent only one single frame of a process that takes longer than most human lifetimes to complete a full swing from one extreme to the other. A season no single human observer has ever watched unfold from beginning to end. Researchers analyzing the data later identified fields of dunes on parts of Sputnik Planitia, hundreds of parallel ridges stretching across several thousand square kilometers, formed not from sand the way dunes form on Earth, but from tiny wind-blown grains of frozen methane ice. What made the discovery genuinely surprising to the scientists who found it wasn't simply that dunes existed on Pluto, but that they existed at all, given how astonishingly thin Pluto's atmosphere actually is. Moving sediment into dunes requires a minimum threshold of wind strength, and Pluto's atmospheric pressure is so low that most researchers assumed its winds simply couldn't be strong enough to do the job. The dunes suggest otherwise, likely aided by Pluto's weak surface gravity, which lets lightweight ice grains stay airborne far longer once they're lofted into motion by sublimating nitrogen ice nearby, making even Pluto's famously thin air capable of shaping the landscape in ways nobody had modeled beforehand, perhaps the single most provocative idea to come out of the mission, though remains the least directly confirmed, and it's worth being upfront about exactly how much of it is still genuinely open. Sputnik Planitia sits almost perfectly aligned with the tidal axis connecting Pluto and its largest moon, Charon, precisely the location where you'd expect an unusually dense concentration of mass to naturally accumulate over time if Pluto's rotation and orientation had gradually reoriented itself around that extra weight. A basin filled purely with low-density nitrogen ice shouldn't be dense enough to account for that kind of gravitational realignment on its own. Researchers, including a widely cited 2016 study led by planetary scientist Francis Nimmo, proposed that the missing mass could be explained by a layer of liquid water sitting beneath the ice shell denser than the nitrogen ice above it, effectively an ocean hidden under Pluto's frozen crust. A follow-up study published in 2019 by researcher Shunichi Kamata and colleagues went further, proposing that this hidden ocean could plausibly have remained liquid since Pluto's formation, insulated from freezing solid by a layer of gas hydrates, essentially frozen cages of trapped gas molecules acting as a thermal blanket between the ocean and the surface ice above it, slow enough at conducting heat outward to keep liquid water stable for billions of years, despite Pluto's punishing surface temperature. If that model holds up under further study, and it remains a genuinely contested hypothesis rather than a confirmed fact, it would mean Pluto has quietly maintained a body of liquid water, sealed away in total darkness beneath dozens of kilometers of ice for nearly the entire history of the solar system, a reservoir of liquid water older than complex life on Earth, warmed not by sunlight, but by nothing more than the faint residual heat still leaking out of Pluto's core. That kind of isolated, sunless, purely chemically driven environment is exactly the profile astrobiologists have grown increasingly interested in over the past few decades, ever since researchers began documenting thriving microbial ecosystems clustered around hydrothermal vents on Earth's own ocean floor, communities of organisms that draw their energy entirely from chemical reactions rather than sunlight, and entirely independent of anything happening on the surface far above them. Nobody studying Pluto is currently claiming there's life inside a hypothetical subsurface ocean nearly 4 billion miles from the Sun, and it would be scientifically irresponsible to suggest otherwise given the current genuinely thin evidence. But the fact that a serious peer-reviewed hypothesis about a potentially ancient liquid water ocean exists at all on a world once dismissed as a frozen, geologically dead leftover says something meaningful about exactly how badly that original picture of Pluto missed the mark. Pluto's story doesn't end at its own surface either, because its largest moon complicates the picture in its own right. Charon measures roughly 1,212 kilometers across, more than half of Pluto's own diameter, an unusually large ratio compared to almost every other planet and moon pairing in the solar system. Rather than Charon simply orbiting Pluto the way most moons orbit their planets, the two bodies actually orbit a shared point in empty space that sits outside Pluto's own surface, locked in a mutual gravitational dance, each permanently showing the same face to the other as they spin. Some planetary scientists have suggested Pluto and Charon are better described as a binary system than as a planet and its moon in any conventional sense. Charon has its own striking surface features too, including a massive equatorial canyon system with chasms in places running more than 5 times deeper than the Grand Canyon, and a dark reddish cap over its northern pole, informally named Mordor Macula, that researchers believe forms when methane gas escaping from Pluto's thin atmosphere drifts across space to Charon, freezes at its cold pole, and is then chemically transformed by ultraviolet sunlight into the same reddish tholins, coating much of Pluto's own surface. Meaning Pluto is, in a very real and ongoing sense, slowly painting its own moon. 4 smaller moons, Nix, Hydra, Kerberos, and Styx, round out the system, each one small, irregularly shaped, and tumbling through space with genuinely chaotic, unpredictable rotation, a consequence of the complex, constantly shifting gravitational field generated by the Pluto-Charon binary itself. All of this eventually forces the same uncomfortable reckoning, regardless of which specific feature you focus on. The 2006 decision by the International Astronomical Union to reclassify Pluto as a dwarf planet, stripping it of full planetary status after 76 years, was primarily a taxonomic argument about definitions, specifically whether Pluto had sufficiently cleared its orbital neighborhood of other debris the way the 8 recognized planets have. Alan Stern, the principal investigator who spent decades pushing for and eventually leading the New Horizons mission, has been consistently publicly critical of that reclassification ever since, arguing the definition used was poorly constructed and inconsistently applied. That particular argument remains genuinely unresolved within the planetary science community, and reasonable experts land on different sides of it. But whatever the outcome of that specific naming debate, the geological data New Horizons actually returned settled a separate, more scientifically consequential question entirely. Whatever you choose to call Pluto, it is not a simple, inert leftover chunk of solar system debris. It's a genuinely active world, still visibly reshaping itself through mechanisms scientists don't yet fully understand. There's a broader implication tucked inside all of this that extends well beyond Pluto itself. Pluto is just one member of the Kuiper Belt, a vast ring of icy debris beyond Neptune's orbit, stretching from roughly 30 to 50 astronomical units from the Sun, home to an estimated hundreds of thousands of similar icy bodies, the overwhelming majority of which have never been visited or photographed up close by any spacecraft at all. Before 2015, the reasonable working assumption was that Pluto, as the largest confirmed object in that belt, represented something close to a best-case scenario for geological interest out there. And if even Pluto turned out to be this dynamic, the assumption ran smaller, more distant Kuiper Belt objects were almost certainly less interesting still. New Horizons findings arguably scramble that logic entirely. If the object researchers were most confident would turn out to be a frozen, inactive relic instead turned out to be actively convecting, potentially volcanic, and possibly hiding a liquid ocean, it raises a genuinely open question about what similarly sized, similarly distant bodies like Eris, Makemake, Haumea, or the far more distant Sedna might be quietly doing as well, entirely unobserved, simply because no spacecraft has ever been sent close enough to look. There's a broader pattern worth sitting with here too, one that stretches back well before New Horizons ever reached Pluto. Voyager 2's 1989 flyby of Neptune's large moon Triton, an icy world with a surface temperature and composition strikingly similar to Pluto's, unexpectedly revealed active geysers erupting nitrogen gas and dark material several kilometers into its thin atmosphere, a discovery that at the time was treated as a strange, isolated exception rather than a preview of anything broader. That comparison carries an extra layer of significance, since many planetary scientists suspect Triton may actually be a captured Kuiper Belt object itself, gravitationally seized by Neptune sometime in the distant past, rather than having formed as a natural moon in place, meaning Triton and Pluto may effectively be close cousins, similar bodies that ended up on very different orbital paths. Cassini's exploration of Saturn's small moon Enceladus later revealed genuine water ice plumes erupting from its south pole, feeding one of Saturn's rings. Titan turned out to host entire lakes and rivers of liquid methane under its thick orange atmosphere. Each of these discoveries arrived as a genuine surprise to researchers who had, going in, expected comparatively little from a small, cold, distant world. Pluto simply continues that same pattern, one more entry in a growing, increasingly hard to ignore list of icy bodies that turned out to be far more active and complex than the conventional wisdom predicted before anyone actually looked closely. There is, at least in principle, a path toward learning more, though it remains entirely conceptual for now. Scientists and mission planners have discussed the possibility of a dedicated Pluto orbiter, a spacecraft that could remain at Pluto over months or years rather than racing past in a matter of hours, capable of watching the system change across its full 248-year orbital cycle rather than capturing a single frozen snapshot of one particular season. One informally discussed concept, sometimes referred to as Persephone, would carry instruments specifically designed to measure the thickness of Pluto's icy shell and search directly for the gravitational signature a genuine subsurface ocean would leave behind, potentially resolving the ocean question that New Horizons could only gesture toward indirectly. As of now, no such mission has received formal funding or a confirmed timeline, and given the distances involved, any future mission would likely spend well over a decade simply in transit before it ever arrived. But the case for eventually sending one has only gotten stronger with every year. Scientists have spent poring over New Horizons' surprisingly rich 16 months worth of transmitted data. What makes Pluto's story genuinely unsettling to sit with, in the end, isn't any single discovery on its own, striking as each one is individually. It's the scale of how completely wrong the prevailing scientific consensus turned out to be, and how confidently that wrong picture had been held for decades before anyone actually bothered to check it up close. For most of the 20th century, Pluto was treated as a settled, unremarkable footnote, small enough and far enough away that nobody seriously expected it to challenge anything fundamental about how planetary science understood heat, geology, and the long-term fate of small, distant worlds. It took one 9.5-year journey and a handful of frantic hours of close-range imaging to demonstrate just how badly that assumption had missed the mark, and to leave researchers with genuinely open questions about internal heat retention, cryovolcanism, and a possible ancient ocean that remain unresolved to this day. Somewhere out past Neptune right now, in near total darkness, roughly 6 billion kilometers from the Sun, Pluto continues doing exactly what it's apparently been doing all along, quietly reshaping itself in ways science still can't completely explain. If stories like this pull you in, subscribe to the channel, because this is exactly the kind of territory we spend our time exploring here. Drop a comment and tell me which part surprised you most. The nitrogen ice plain that's still actively convecting after 4.5 billion years. The possibility of a liquid ocean hidden beneath the ice, or the idea that Pluto might be quietly erupting through genuine cryovolcanoes. Let me know where in the world you're watching this from. And if you want to keep exploring, there's another documentary waiting for you right here on the channel. So stay a little longer and let's keep looking out toward the edge of everything we thought we understood.